Okay, great. And thanks again for joining us here today again for serverless streams, topics, queues, and APIs, how to pick the right serverless application pattern. Again, my name is Chris Munz. I'm currently a senior and technically the lead developer advocate for serverless based out of our New York City office here for Amazon. I've been at Amazon for a little over 6 years now across a number of different roles, but for the last year and a half have been focused on the space of serverless and working with our developer customers in understanding what it means and how to build applications and build them well and understand development workflow and things like that in the space of serverless. So why are we here today? So this realm of serverless applications and serverless infrastructure is incredibly popular today and growing more popular seems every day here. But there are a lot of aspects to it that are unique and new for people, particularly when it comes to, from an architectural perspective, of how to design your applications based on how you should essentially invoke them. Now, when we talk about serverless here at AWS, there are a couple criteria to what it is that we define as something being serverless. First is there's no servers to provision or manage. So no physical servers, no virtual servers, no containers that you yourself would have to think about managing in any way, shape, or form. Now, as requests come in, as data comes in, as records come in, a serverless product should automatically scale with usage and be able to handle that load and respond to those queries or, again, messages, records, etc. You should never have to pay for idle. So going along with the automatic scaling for usage, you should also never have to think about capacity management. And so typically in an infrastructure where you are dealing with what I consider to be a more server full methodology, you are thinking often about the capacity that you need and having that available. Whereas with serverless, you never have to think about paying for idle because as requests come in, we will be able to scale up the resources for them. And again, it's not something that you should have to think about. And then lastly, availability and fault tolerance built in. So here at AWS, we have a concept of regions. Inside of those regions, then we have a concept of availability zones. You can think of these as separate data centers that exist inside of a given geographic area, where they're separated typically by a couple miles or so. And one of the most common architectural best practices at AWS is to build your applications across multiple availability zones inside of a given region. And with our serverless products, this is something that's actually going to be handled for you so that you don't have to think about this architectural concept yourself. At the center of the world for serverless here for us at AWS is a product called AWS Lambda. Now, AWS Lambda is a compute product. And what Lambda allows you to do is to write your application, your business logic, your code, whatever it is that your application needs to do in one of the 5 languages that you see supported here, Node.js, Python, Java, C#, and Go. And essentially configure an event source, which is where we're focusing most of our time on here today, such that it will trigger this Lambda function to execute your business logic in your code that will then go and perform whatever it is that it needs to do. So maybe this is talking to databases or data stores. Maybe it's talking to other APIs or endpoints that exist inside of your infrastructure. Essentially, at that point, it is your code and your logic that is executed. Now, Lambda, again, is a compute service. So it itself is managed on top of underlying compute resources. Yes, there are servers and serverless, but again, you don't have to think about them. You don't have to manage them. You don't have to scale for them or pay for idle for them or deal with high availability when it comes to thinking about Lambda. Now, as per kind of the focus of today's webinar, we're going to be focusing primarily on some of the different event sources that exist out there that you could use to trigger your Lambda function. And essentially, again, when we think of the serverless application, it's the event source, the function, and then what it is that the function needs to do or maybe talk to. But when it comes to an event source, there's many different options that are out there, and there's many different ways that you can architect your application. And so today we're going to be focusing on 4 of those. And really kind of talking about the differences between them and how you should think about selecting one versus another. Now, when it comes to use cases that exist for serverless and for Lambda in particular, there are a number of use cases that we see as very common patterns. Web applications, so typically APIs that would power static web applications or even more complex web applications out there. There are backends, so backends that might be, say, internal microservices. They could be backends for mobile applications or IoT connected devices. Data processing, so real-time data streaming and analytics, MapReduce, batch processing of various bits of data, also a very, very popular use case. Chatbots, pretty straightforward. We see chatbots showing up all over the place these days, both for internal and external use cases at organizations. I've seen chatbots that help people get sales, and I've seen chatbots that help people deal with, say, internal business resources like facilities or HR, or something similar to that. Amazon Alexa. So Amazon Alexa is a voice-powered AI, if you could think of as it were, that lives inside of many different types of devices. And the Alexa team says that the best way to host Alexa skills, essentially the various capabilities that Alexa has, is with AWS Lambda. And so quite many of the Alexa skills that you might interface with if you have an Alexa-enabled device are actually managed and hosted on top of Lambda. And then lastly, IT automation. So IT automation covers a pretty wide breadth of space, I would say, things like policy engines, responding to infrastructure events, glue between various different AWS, say, development or management tools. And it's typically one where we see a lot of our customers initially dip their toes into using Lambda, but it really kind of makes up the long tail of usage, as it were, for the platform. Now, in terms of today's conversation, we're really going to be focusing on essentially the services or the architecture for three of these: backends, data processing, and IT automation. Now, when it comes to web applications, those are pretty much often straightforward API-based services where you would have an API gateway talking to a Lambda function. For chatbots, you're probably using some sort of chat service like Amazon Lex, or with Alexa, you're using Alexa voice service to interface with a Lambda function. But when we talk about backends, data processing, and IT automation, this is where there's actually, I think, a lot more in terms of the various types of architectures that we'll see customers build for. Now, when it all comes to kind of being thought of from a big picture, the term microservices comes up quite a lot. Here at Amazon, across the whole company, not just AWS, we actually have a very long history of building what today would be considered microservice-based applications. This kind of Death Stars looking diagram that you see here shows up in a lot of our DevOps and microservices related presentations, and actually it represents all the services that were inside of Amazon about circa 2008, 2009. And so internally as a company, we've been building microservices for well over a decade now, have a lot of honed best practices. And what I would say is that over maybe the last 4 to 5 years, what we've seen is the customers of AWS is kind of an explosion in those companies building microservices as well. And so we see large companies such as Netflix and Capital One, we see smaller startups, we see more traditional businesses all going down this route of microservices. Now, typically when people talk about microservices, they often talk about REST-based microservices, or those that might be available over some sort of API. And that is still probably the most common pattern that we see out there, essentially where you would have, say, an API gateway, such as Amazon API gateway, that in the case of a serverless API would invoke a Lambda function, and then that Lambda function would go and do again whatever it is that it needs to do. But there's something that I like to call the microservices iceberg. And what we see when we work with customers is that quite often what the iceberg represents is a collection of microservices that represent a overall product or an overall business's compute resources. And very often there is some sort of public interface. This is typically the thing that, say, we'd be talking to a web application or a mobile application, something similar to that. And then behind the scenes, or kind of below the waterline, would be all of the internal services that that organization has built that power whatever it is that that business needs to do. And so the reality in the microservices world is that actually very few services often need a public-facing API. And in fact, if you're controlling all the various services that are being built and you have some level of organizational standards and communication that can be in place, quite often you don't need to build an API between two private internal services at all. And so what we often see is that there are other options for talking between services inside of a microservices architecture that aren't just traditional APIs, or in this case, bespoke APIs that you yourself might be building. And so we're going to talk today about some of the services, again, that you could put between various different services, or I should say the various different ways that you can invoke various different services between each other across a number of different AWS services. And so essentially focusing on what it is here that is below the waterline of this iceberg. So with Lambda, we have a number of different execution models that we support. We support a synchronous push-based model. In this case, with something like Amazon API Gateway, where a call is made to the order API, it is going to invoke the Lambda function and then expect a response back, synchronous model. There's an asynchronous or event-driven model, where services such as Amazon SNS or S3 might invoke a Lambda function based on a message being put into a topic with SNS, or an object being put into an S3 bucket. And in this case, it's going to invoke the Lambda function, and we're not expecting the Lambda function to necessarily respond to that service. We're just going to expect it to do whatever it is that it needs to do. And then lastly, there are stream-based models, in this case with examples such as Amazon Kinesis and Amazon DynamoDB, where those services are going to send out a stream of changes to them, such that then the Lambda service will actually pull that, take down those changes or those records or those updates, and invoke a Lambda function on your behalf. So 3 main execution models, synchronous, asynchronous, and stream-based. And now across these live a number of different services that can invoke Lambda functions. But again, today we're going to be focused primarily on Amazon Kinesis Streams, Amazon SNS, Simple Notification Service, Amazon SQS, Simple Queue Service, and then the Lambda API itself. So let's talk first about the Lambda API. So like almost every single service that we have here at AWS, the Lambda service is powered by an API. In this case, it is a public-facing API that you as a customer of AWS can very easily write an application against and interface directly with this service. Now, going back to what I was describing earlier as this microservices model inside of Amazon, the Lambda API is actually what is consumed by other services that can invoke Lambda. So an API gateway wants to invoke Lambda, it uses the Lambda API. When SNS wants to invoke Lambda, it uses the Lambda API. And so in the case of all of the asynchronous and synchronous models, the Lambda API is what is used already today by all of those products. Now, you yourself can actually code an application client to talk to the Lambda API directly without having to go through an API gateway. And so if you don't have the need for some of the more sophisticated capabilities of, say, Amazon API Gateway, you can actually just directly use the client that's included in every one of our SDKs to code your applications to invoke Lambda either synchronously or asynchronously directly without any other sort of middle service. And so I find that this is actually maybe a lesser known or lesser understood capability of the Lambda product, in that you don't necessarily need another service between another application of yours and Lambda in order to handle the invocation of it. You can directly code this and get all the same capabilities as Lambda itself can provide. Now, another option is Amazon SNS, Simple Notification Service. SNS is one of the oldest services that we have here at AWS. It's used very heavily by customers of AWS, both large and small. And so SNS, as we say on the marketing site for it, is a simple, flexible, fully managed, publish, subscribe, messaging, and mobile push notification service for high throughput and highly reliable message delivery. Essentially what it means is that you can publish messages into what's called an SNS topic, and then that SNS topic has the ability to then push or deliver those messages out to services that have subscribed to that topic. Now, these could be HTTP endpoints, HTTPS endpoints, mobile devices, SQS queues, or in the case of what we're talking about here today, Lambda. So as messages are put into an SNS topic, the SNS service can then go and directly invoke a Lambda function with these messages, and then your Lambda function can consume that message or that record or that data and execute it. Now, there's a couple of interesting things that SNS can do. One is that it has the ability for you to have multiple subscribers on a given topic. So let's presume that you have a complicated microservices environment. Let's say that you have a checkout process. You could put in a, say, message into an SNS topic that says that an order was placed and have that be consumed by, say, a credit card processing service, a shipping service, a inventory service, all of them who are subscribed to this SNS topic that would then get the same message and then act upon it independently from each other, but again, still processing that single one message that was sent in. Now, you can do more sophisticated things on top of this as well, such as filter those messages such that only certain subscribers maybe get some. Maybe let's say that at some point somebody cancels an order and you only need to update some of those services. So you can set to only filter based on, say, new orders being processed. So a number of different capabilities here of SNS, but again, a service that is integrated very deeply into the AWS platform today. Amazon SQS, or Simple Queue Service, again, as we say on the product site here, is a simple, flexible, fully managed message queuing service for reliably and continuously exchanging any volume of messages from anywhere. Again, to put it more simply, it's a managed queue service that allows you to publish messages into it. The Lambda service then can pull a queue looking for new messages, and when it finds messages, we'll grab them and invoke a Lambda function on your behalf. Now, SQS is technically the first web service that Amazon ever launched. It goes way, way back before actually technically there was AWS as a business inside of the company. SQS is used very heavily internally at Amazon, at AWS, and by customers of all shapes and sizes to do massive throughput and massive velocity of queued messages and queued message delivery. Now, in regards to using Lambda and integrating with Lambda, it is pretty straightforward. You basically point it at the queue, and what happens is the Lambda service maintains a puller that pulls the messages out for you. Now, those messages are processed in batches, and you get to define that. And then basically your Lambda function would then consume those batch messages and act upon them as necessary. Now, with SQS, we say that it has at least once delivery. There is the potential for a message in an SQS queue to be consumed by more than one reader. Now, SQS as a large distributed system, it really favors durability and availability of the service. But what can happen potentially, although it is incredibly rare, is that messages could be pulled out more than once. And so you do have to think about the idempotency of the messages inside of your system and how that could impact things. And then lastly, Amazon Kinesis Streams. So Kinesis Streams is a fully managed, highly scalable service for collecting and processing real-time data streams for analytics and machine learning and really all sorts of use cases. The way that it works with Kinesis is as data is put into a stream, again, the Lambda service will pull that stream looking for changes and looking for new records being put in. It will pull those records out and inject them into a Lambda function via an invocation. Now, Kinesis is a really great product that has a lot of different capabilities to it as well. It is meant for really massive throughput of ingest of data, potentially terabits per second of ingest. And so with Kinesis, you create a stream. Your stream is then consisted of shards, which have a fixed amount of capacity and throughput. And then Lambda will receive batches of messages off of those streams off those shards, I should say, in parallel. Now, much like how SNS supports the ability of a fan-out model for sending messages to multiple receivers, what Kinesis allows you to do is have multiple consumers off of the same stream such that you could have individual applications that are all pulling in the same data. Now, in this case, there isn't really a way for you to filter those messages out such that you could prevent one application that's consuming a stream from getting some messages versus another. But this does support the ability for you to basically do very interesting multiple application path workloads, I would say, for things like near real-time analytics and data processing. So 4 different models, bunch of different nuances to them. How can we go about thinking about how to compare these various services? So there's basically 6 criteria that I came up with for us to think about. And there's definitely other things that we could talk about in terms of, say, complexity of the model for processing the events, for how the events are potentially processed or sent into your Lambda function. But essentially what I want to focus on here today are these 6 criteria, which I find are probably the biggest things that help drive how people think about which of these services they would consume. So we're going to talk about scale and concurrency controls. We're going to talk about durability of the data inside of one of these services. We're going to talk about the persistence of the data inside of these services. Then we'll talk about the consumption model and how you can think about how applications take data out of these services. We'll talk about failures and retry handling. And then lastly, we'll talk about pricing, which is definitely a factor that people are going to want to think about. And now what I've done here is unfortunately not the prettiest of slides, but it's going to break down in chart form how you can think about comparing these 4 services or these 4 capabilities against each other. So let's get started. So when it comes to scaling and concurrency controls, at times you want to think about what is possible given one of these services. Now, all of these services are meant for massive, massive, massive concurrency. And in fact, there are AWS customers that are using all of these services or using each of these services in some way at really incredible scale. So you should feel confident that for almost any workload out there, you can make one of these services handle the concurrency and scale required for your business. Now, one aspect also about this is that there are times where you actually want to control that scale and that concurrency. You might want to protect downstream resources. You want to make sure that maybe you're not consuming data too quickly. And so the ability to control that scalability is also a concern that you want to take into account. Now, with the Lambda API, the way that Lambda measures concurrency is just basically in the invocations that are happening at any point in time. And so it is not a per second or a per minute time-bound period. It is just the raw concurrency at any point in time. And so for each individual function, you have the ability to control this concurrency via something that is called a per function concurrency throttle. And so this allows you to actually say how much maximum concurrency you want a function to consume. And so this can go from 0 all the way up to the maximum total amount for an account in a given region. However, it is shared across all of the functions that are in the account in that region. So today, by default, you get 1,000 concurrency. And if you had 10 functions, you could give each of them 100. You could give each of them 10 and then have a whole lot left over. You could basically cut it up however you wanted with the max combined concurrency, though, of 1,000 within the account. And again, that 1,000 is just the default. You can make requests to get much higher. For SNS, the service itself automatically scales. You never have to think about what's involved in scaling an SNS topic. And so when it comes to consumption of data out of SNS, the Lambda per function concurrency setting is really the only way that you could say how quickly you want to consume data from an SNS topic. With SQS, very similarly. So the service itself is just going to scale. You never have to think about turning any knobs or levers in order to make SQS scale up. And now when it comes to the Lambda integration, you define the batch size, so the number of records that are going to come as part of a single invocation payload. And then you can also then configure the per function concurrency setting to control, again, any downstream consumption or impact to underlying services. Now, Kinesis is a little bit different. With Kinesis today, you do have to think about the number of shards that you have in a stream. And so a single shard provides an ingest capacity of 1 megasecond, or about 1,000 records per second. And then an outbound of up to 2 megabits per second of data. So basically what this means is that you can actually read from Kinesis slightly faster than you can write to it. Now, if you have multiple consumers off of a single stream and off of the same shards, they will take basically against that total of 2 megabytes. And so that's why the output level, number is higher than the input number is. So again, across these 4 different models, with Kinesis, that's the only one that you have to think about the maximum capacity or throughput of the underlying service. With SNS and SQS, it's going to automatically scale up to handle as much data as you can throw at it. And then with the Lambda API itself, concurrency is a factor of the total concurrency that your account has, and then what you configured the function itself for in terms of if you have configured a per function concurrency throttle. So I talked about this a little bit here already, Lambda per function concurrency throttles. Again, this is a shared pool inside of an account per region. You do have the ability to configure this per function. So you can either not configure it or configure it. And essentially what it does is it acts as a reservation against that total capacity number. And so this can be really important for, again, protecting downstream resources, for things like cost control, for helping to make sure that you're providing, say, a even ability for resources to talk to downstream resources, as well as to allow many different Lambda functions inside of your account to all be able to be executed without, say, starvation of the total concurrency. Lastly, you can actually also use this as what we consider to be kill switch. Essentially, setting a function concurrency to 0 will stop a function from executing without you, say, having to modify the trigger or the function itself to do something different. And so setting per function concurrency controls makes a lot of sense to even just set it high and just have something there that acts as basically an upper bound on what it is that a Lambda function could end up doing. Now, when you think about concurrency across models, you want to think about in terms of what parallelization looks like and kind of order of operations for consumption. Now, when we talk about SNS or just the Lambda API in a synchronous model, basically messages or invocations are going to go at the Lambda service and be pulled off in kind of almost an ordered sense. SNS says that it makes best attempt to deliver messages in the order that they were received. And so in this case, there isn't really anything in terms of batching that really happens. You're just going to pull those messages off. With queue-based, you have the ability for messages to be brought into the queue and then processed in technically any order that they've been received in. And so you can actually have a queue that builds up data, let's say, that builds up requests, and then periodically turn on a Lambda function such that it can consume it. And this is not an unusual model. We actually see customers that want to do this very often, where they want to batch up data over a period of time in a day, and then essentially process it all down from the queue over a period of time. Now with stream-based, it's a little bit different. Essentially, you get the same model as queue-based, but parallelized. And so given that the streams are then made up of shards, and shards will have individual messages being put into them, a given Lambda function invocation is only going to process data from a single shard inside of the stream. And now with Kinesis, it will pull down batched records and it will process those batches from that stream. What's great about this is that inside of a stream and then technically inside of a shard, you will have order, essentially chronological order of the messages or records as they are put into that individual shard. And so ordered data inside of a shard will always show up in the order that it has been put in. So this can be useful for things like capturing, say like click traffic or capturing log information, where you want to make sure that you are consuming those in the order that they were sent. Now, one last bit here about concurrency is understanding the difference between concurrency and latency. When it comes to processing data off of these services, customers are often very much concerned about what is the latency between record ingest and record consumption. Now, this is sometimes a factor of the concurrency of the Lambda function. It can also be in the example of where you might have set a per function throttle. It also could be a factor of, for example, the amount of data that is put into a given resource. So for example, when we talk about stream-based invocations, in the case of at least Kinesis streams, you have a maximum theoretical throughput of the number of shards times 2 megabits per second. In this case, because of the theoretical, or because of the maximum output of a given shard of 2 megabytes times the number of shards that you have, this is how much data you could potentially ingest. And so if you are putting in way more data than you could potentially pull out over time, then what this can effectively mean is that the latency in processing the data will increase. Now, when we talk about the effective theoretical throughput versus the maximum theoretical throughput, there's also a factor here in terms of the duration of the function execution, as well as potential for retries until expiry. Now, this gets a little ahead of ourselves here, as we're going to talk about retries and failure scenarios here in a little bit. But basically what it comes down to is if you are putting in way more data into the resource than you have the ability to consume on the downstream side, it's going to increase the perceived latency of processing those records. So it's not necessarily just about how much time it takes for the service to ship the data from point A to point B, but it's how long it takes for you to actually process that, how quickly you're pulling it off of that resource itself. That is a factor here. Now, that's primarily for the streaming-based services like Kinesis Streams. For the other services, really what you're talking about is the maximum concurrency divided by the average duration effectively gives you the events per second. Now, this is a little bit more straightforward, I think, than it is with streaming. So for example, if I am pulling messages from a queue and I have set that my maximum per function concurrency for my Lambda function is set at 10, and it takes a second for each of my functions to execute and do what they need to do. Essentially, I'm not going to be able to do more than 10 requests per second effectively off of that queue. Now, this isn't a factor of the queue scalability or what it can handle. It's more about my application and what it can do. So thinking about concurrency versus latency is an important aspect when it comes to performance, and definitely something that you want to calculate into how you decide which of these products you'd use. So next up, we'll talk about durability. And so when we're talking about durability, we're talking about what happens once the request has been accepted by one of these services until it's been processed, essentially while it's in flight, while managed by that service. Now, with the Lambda API, there's really no concept of durability. The service itself is highly available and built to the best of practices that we have here at AWS for making a service available and scalable. But essentially, when requests come into it, it's going to immediately try to process those requests, there's really not a concept of it storing those requests until they've been processed. In this case, a client would need to handle any sort of failures or retries that might occur. Now, for the rest of these services, though, SNS, SQS, and Kinesis streams, durability is a factor of those products. So for SNS, we see that it provides durable storage of all the messages that it receives. Essentially, any message that it gets, it will then store multiple copies of across multiple availability zones before it ever acknowledges the receipt to the request of the sender. Amazon SQS, very similarly, stores all the messages in queues and messages within a single highly available AWS region across multiple AZs, such that there's basically no single point of failure. And then Kinesis Streams also replicates data across at least 3 availability zones, providing high availability and data durability. Really, the takeaway from this one, the short version, is that for SNS, SQS, and Kinesis Streams, data is going to be replicated across multiple availability zones and stored with a high level of durability such that no single point of failure should cause any record to be lost while it's in flight. Essentially, if you get back a 200 OK when you talk to the APIs for these services, you can have the comfort that your data is securely stored in them until it's been processed and pulled back out the other side. Now, durability is one thing, but persistence is something a little different. Now, persistence is basically the idea that the service will hold on to the data and potentially keep it available for a longer period of time, essentially the length of time of the request being in flight. Now, you might think to yourself that you want requests to be handled as quickly as possible, and in many use cases, that is the truth. However, there are times when you have to think about, say, in the case of a failure, what has happened to the request? What has happened to the data in the request? So persistence in this case matters just as much as durability, in the sense that if my downstream service has a problem, I want to make sure that it's going to continue to hold that data for me until I have fixed my problem. So with the Lambda API, there's no formal persistence model. Essentially, again, if you have made a request to the Lambda service and it has accepted it, it is going to attempt to, handle that invocation for you, and we'll talk about the retries here in a little bit. Otherwise, it is going to offer up a failure, but there is no essentially storage capability inside of the Lambda service for requests while they are in flight. For SNS, it's also similarly, it's basically the same kind of concept. Essentially, there is no persistence model beyond the delivery retry logic. Now, the delivery retry logic, which we'll talk about here, actually extends up through potentially 13 hours of time. Now, this isn't something you would want to think about using purposefully as much as it is the way that the service handles retries, which again, we'll talk about here in a second. Now, SQS is different here. So SQS by default stores messages for 4 days. So you can write data into an SQS queue without pulling any data out of it for 4 days and then begin pulling that data out. And as long as you can consume that data faster than that, then it could expire in that time frame, then you're okay. Now you can actually modify this and change what's called the message retention period all the way up to 14 days or to as low as 60 seconds. And now there's various different reasons why you might want to think about, bringing that data point down or bringing that time limit down versus bringing it up. And again, one of the things that we see customers often do is put data into a queue that maybe they only need to process every now and then. Or maybe what they do is because SQS is so scalable, they use it as a buffer in front of a service where they don't really know how heavily it might get hit. Maybe you get 10,000 requests per second for a small period of time when you would normally get 10 requests per second. Essentially, SQS is going to be able to handle that bulge of data, store the records, and then you can consume them at whatever rate it is that is necessary or supported by your application. Now, Kinesis Streams, very similar to SQS. In this case, by default, data is stored for up to 24 hours. You can also increase this up to 168 hours, which works out to be 7 days, via something called extended data retention. Now, extended data retention does come at an extra cost of 2 cents per shard hour above the default 24 hours. And we'll talk a little bit more about pricing here in a bit. But essentially, this does give you a longer period of time if you do need to handle replaying data or playing data out across multiple different services that might exist. So again, persistence, different than durability in the sense that this isn't necessarily about that the request has been successfully saved by the service. It's more about how long will it stay available inside of the service's effectively buffer before it potentially goes away. Next, we'll talk about consumption. And so I talked a little bit about this when I kind of gave the intro to the 4 different services. But when we talk about consumption, we're talking about essentially how it is that you would think about consuming records off of, say, the service itself into a Lambda function. Now with the Lambda API, this is basically going to be either a synchronous or an asynchronous request to the service. It is going to result in a single invocation per payload that's being passed in. And it's pretty straightforward from there. There's, again, no concept of multiple clients. There's no ability to do, say, fan out or replays. Those messages are going to be passed in, the requests are going to be passed in, be consumed, and then acted upon. Now, for really complicated Lambda to Lambda workflows, you're going to want to use AWS Step Functions, which I'll talk about here in just a moment. For SNS, SNS is an asynchronous to Lambda invocation model. Again, SNS supports the ability for you to fan out to multiple subscribing Lambda functions with the same message. So again, you could basically treat SNS effectively as a message bus that delivers messages out to various different services effectively in parallel. Now, there are, again, a number of different capabilities with SNS and how it can handle this. You can do message filtering to control which messages go to which subscribing services or which subscribing functions. There's also something called message delivery status, which allows you to track failures of messages that have gone through SNS. I think it's really important to turn this on as it provides a lot of data towards debugging any potential issues inside of your infrastructure. With SQS, so with SQS, Lambda maintains a poller that will poll your SQS queue and takes messages from that queue and then invokes Lambda functions synchronously on your behalf. And so it will then scale the amount of polling that it does based on the number of in-flight messages that the service can detect about your Lambda function, or I'm sorry, about your queue. And now what happens is that synchronous invocation, when the function comes back and tells the Lambda service that it has successfully completed whatever work it is that it needs to do based on your code, the Lambda service can actually then delete the message from the queue for you. If you don't want it to do this, you can actually do this inside of your code as well. And we'll talk about here with retries why this matters in a little bit, but essentially you want your Lambda function to positively report back to the service that it has succeeded, or you want it to clearly fail back to the service such that the messages can be replayed later on. Now with SQS, there is only the ability for a single consumer to ever consume a message at a given point in time. Again, in the case of a failure, which we'll talk about here in a little bit, a message could be replayed essentially later on. But now, while we do say that it really only should ever be a single reader that ever gets it, again, remember that with SQS, you do have the possibility that a message could be delivered more than once. So again, the idempotency of the message and how you consume that message inside of your function itself is important. Now with Kinesis streams, very similar to SQS, they're both polling based. Lambda polls the service on your behalf and takes messages from the Kinesis stream and the shards inside of it, and then directly invokes Lambda functions in a synchronous model. Now in this case, what's typically going to happen is the Lambda function itself is looking, or the polling function is using the Kinesis client library to actually go then and pull the data out and invoke your Lambda function. Now, different from SQS in this case is that you yourself do not need to tell the Kinesis client library that, hey, these messages are good. You just need to tell the Lambda service that your function has completed successfully. And then in this case, it's going to use the AWS Kinesis library on your behalf to report back that the records are processed. Now, one thing that you want to be aware of with Kinesis is that when you configure the trigger, you do configure the batch size. And sometimes, depending on how data was put into Kinesis, it can also have batched records that were put in on the ingest side. And so it's very common that you might pull down a batch that is actually made up of other batch data. Now, depending on your workload and what it is that you do inside of your Lambda function, this could actually lead to highly variable situations where you maybe consume more data than you would expect. I've actually personally worked with a customer that had a lot of variability in terms of how much data they were pulling in via Kinesis stream into Lambda functions, and they would from time to time run into function timeouts due to this variability. So thinking about what effectively your Lambda functions timeout, the max amount of data that might end up in a batch size, and what it is that you do with that data that's been brought in is very important in understanding how you should think about scaling out your Kinesis stream via potentially adding more shards and also configuring the batch size that the Lambda function pulls from. So I mentioned a little bit about this before in terms of with the Lambda API and how you think about things like failure modes and as well as thinking about more complicated workflows. One thing you really want to make sure that you do with your Lambda functions is keeping orchestration out of your code. Essentially, if you have, say, a workflow like you see here in this slide, and you have Lambda code or code in your Lambda function, I should say, that is handling retries, that is handling exponential backoff, that's doing error handling, you're writing a lot of code that you don't need to write yourself. So we have another service here at AWS called AWS Step Functions. It is a workflow management service that is part of the serverless family here. And so what you can do is actually coordinate really complicated business workflows via Lambda functions, as well as actually external services, such that the step function service itself handles things like failures, retries, exponential backoffs, various different decision trees, parallel tasks, sequential tasks, all sorts of sophisticated things that you would otherwise sometimes have to write code for yourself. You could do things like have custom error handling based on your Lambda function output. And so if you find yourself doing things where Lambda functions are invoking other Lambda functions, you might really want to start to look at step functions as a way to properly wrap the business logic that you have with the business workflow. So talking here now about retry and failure handling, even though we touched upon this in a couple of the previous slides, retry and failure logic is client dependent for synchronous invocations for the Lambda API. So if you're doing any coding yourself of the client yourself against Lambda API, you're going to have to be cognizant of how you want to handle failures and retries. For example, with API Gateway, it does not do any retrying on your behalf. It simply passes back that there was a failure in the API call, and then it's up to your client logic and how you'd want to handle that going forward. Now for asynchronous though, invocations are retried twice by the Lambda service. So there is the potential there that, let's say that you did some work inside of your function and then it timed out or it failed for whatever reason, that a invocation could get retried where some of the execution that already happened of that payload or of that data could happen again. And so much like the potential for more than once delivery in SQS, you do want to think about how with asynchronous invocations, if your payload and the work that you're doing can handle that potential for a replay. Now with SNS, and this is taken directly from the SNS documentation, if the Lambda service is not available, SNS will retry 2 times at 1 second apart, then 10 times, exponentially backing off from 1 second to 20 minutes, and finally 38 times every 20 minutes for a total of 50 attempts over more than 13 hours before a message is discarded from SNS. Now, going back to when we were talking about the persistence of SNS and the service itself, this is where that 13 hours metric came from. Now, again, in this case, what's happening is the service itself is going to continue to retry to deliver a message to the Lambda service. And only after this longer period of time and so many attempts will it actually then fail and discard the message from SNS. Now, this isn't the same thing as being able to configure persistence in SQS and Kinesis streams. This is more just the way that SNS wants to try really, really hard to get the message to your Lambda function successfully. Now, with SQS, messages remain in the queue until they are deleted. There is a total period of time, which we talked about before, for the persistence of those messages. But otherwise, in typical workloads, they will stay there until they are deleted. Now, they are prevented from being accessed by other queue consumers during a period of time which is known as the visibility timeout. Essentially what this means is as soon as a message has been delivered to a Lambda function, the visibility timeout counter starts, and you can set this timeout yourself. Let's say that you set it for 30 seconds. That essentially means that the Lambda function then has up to 30 seconds to report back to the SQS service that by deleting the message out of the queue itself. Now, the SQS poller will handle that deletion for you based on getting back that an invocation was successful of messages that it interjected into the service. Or again, you can, inside of your own application code, call the delete command for the SQS API and delete these messages. Now, if something goes wrong and your Lambda function times out, or it fails, or it's unable to, for whatever reason, to successfully complete, and that 30-second window of time passes, then SQS makes the message re-available again so that it can be processed. And so in this case, then another Lambda invocation can happen. The message will get pulled out of the queue and injected into that function and then executed upon. And so again, this is where you want to make sure you want to think about the idempotency of the messages that might be going in and making sure that if there is potential for some of them to be replayed, that that's not going to have an impact on your data downstream from there. And then lastly, with Kinesis streams, the way that it works in the Lambda service is that when it's using the Kinesis client library, the KCL maintains a checkpoint or a cursor against the data that is in a given shard, such that if there's any failures in the processing of that, it will essentially replay the same data point over and over again until the KCL has reported back success in processing those records. And so in this case, the retry and failure handling is built into the Kinesis stream. Now, one interesting thing about this that you have to watch out for is that if you have configured your Lambda function to always consume the oldest record first inside of your, or the oldest record that has not yet been successfully processed inside of your Kinesis stream, effectively what is called trim horizon, then you do potentially have to worry about a bad record that causes a Lambda function to fail, causing it to continue to fail over and over again. And so this is something that I've actually personally seen with code that I've written where my Kinesis handling code didn't handle it well and it would fail. And until I repaired my code, it was unable to process that record directly. And again, this is by design with Kinesis to make sure that the data is safely processed at some point. And it will do this up until the time where the data times out of the Kinesis stream based on the data time limit that you've configured for it. Again, that's 24 hours by default, or if you have extended, it could be up to 7 days. One thing I want to talk about here is Lambda dead letter queues. So I mentioned in the previous slide that by default, an asynchronous Lambda invocation is retried twice. What I didn't mention is that after that event has been discarded, it's possible for you to actually capture it via something called a dead letter queue. Now, a dead letter queue is terminology often used when you talk about queuing systems. Essentially, what it means is that you can establish effectively a catch-all for failed messages that haven't been processed properly. Now, in the case of Lambda, again, with asynchronous invocations, you can capture those failed invocations and send them on to one of two places, either another SQS queue or an SNS topic, where you can then take further action upon them. My recommendation is always turn this on. Especially for asynchronous use cases where, unlike say stream-based, where it will attempt to continue to replay a stream, or like synchronous-based, where you handle this logic in the client, with asynchronous workloads, this is basically the best safety net that you have for capturing failures. And so my other recommendation is actually to put this into something like an SQS queue. So that you can then basically have, say, another Lambda function that reports on that queue or pulls data off of that queue and then attempts to execute some sort of recovery or alerting you that there is some sort of an issue. Another thing you can do is you can actually just set a CloudWatch alarm that gets tripped anytime that the queue length is above, say, 0. And that will help give you, again, an idea that something has gone wrong. And now this could be really useful in situations where maybe you deployed code and you broke your Lambda function. And in the case of asynchronous workloads, where let's say you're processing data from, say, an SNS topic, you may not be able to capture those failures in any way that you could replay them. And so if this data that's going into the function is important to you, if the messages or records that are being sent in matter, you want some way to be able to capture and replay those. And so the dead letter queue is going to give you that, again, kind of bucket catch-all in case things go boom, such that you can hopefully have some way to replay this information and save the invocation data. The last thing I'll talk about here as a factor towards comparing these products is the pricing. Now, the pricing with these products is all pretty similar. For the most part, it's a per request model. With the exception of the Kinesis streams, you also pay per shard hour. So depending on the number of shards that you have in a stream, there is a per hour charge for these. Now, for the Lambda API, this is something that you're going to be paying for no matter what, actually, depending on your invocation source. So if you have SNS going to the Lambda API, you are going to be paying for, in this case, just the SNS message. But in the case of SUS, you're going to be paying for the pull requests in terms of the pulls that are happening, as well as then the Lambda function execution. So that is something to be aware of in terms of the overall cost of the platform. Similarly, with Kinesis streams, you'd be paying again for the shard per hour, as well as something that's called a put payload unit. And so you see here under the factor column what a put payload unit represents. And so depending essentially on the size of the payload being pulled out, the units for that have a given cost, as well as then the Lambda function invocations. Now, one thing that I did not put into here is that for Lambda, you also end up paying for the overall Lambda service itself. In this case, that is a factor based on the amount of memory that you've configured your Lambda function for times the duration of execution. In this case, I was focused really primarily just on the cost for the invocating service itself. Now, with Lambda, SNS, and SQS, you do get 1 million requests for free per month in perpetuity. So for a lot of workloads, especially those that are in the IT automation side of things, this could basically cover, a pretty healthy workload for most customers. And again, makes it really easy to get started and play with and explore these technologies. So we've kind of gone through here a whole bunch of different information in a really quick period of time in terms of how to compare these various 4 different models for invoking your Lambda functions. We've talked about the scale and concurrency controls. We've talked about the durability of the messages when they hit the system. We've talked about the persistence of those messages over a period of time. We talked about various consumption models and the services that support, say, multiple consumers or fan-out models. We talked about how failure and retry logic plays into these various services. And then lastly, we talked a little bit here about the pricing and the comparison for those. So what do you take away from this? Essentially, what is it that you should do? Again, there are a number of things here that you have to think about. When it comes to what people consider to be real-time processing, how real-time is your need? Now, when we talk about SQS and SNS and Kinesis, all of these are going to get messages to you in a very quick turnaround. We're talking here typically milliseconds, at most seconds. So for many workloads, seconds of delay is completely realistic, totally fine, and not going to impact things. Another thing to think about in relation to this is how synchronous are your synchronous workloads? Quite often, I've seen applications where one could effectively hide a synchronous workload behind an asynchronous workload that then has some sort of polling mechanism to look to see that work has been completed. And that could be completely fine for a service as well. Another factor or another thing to think about is, does order matter? Some of these services are going to give you requests in order. Again, Kinesis is going to order data that's come into a given shard. SNS again makes best effort to provide data in order. However, SQS does not. And so that is something you'd have to think about. Do multiple services need to feed off of the same data? Essentially, do you need multiple consumers or do you need fan out? If you do, then you're going to want to think about Kinesis or SNS. If you don't, then SQS or the Lambda API could be just fine. One really key thing here is what happens when you break your Lambda function? What is the impact that could happen by, say, just a bad code deploy? Bad code deploys happen. It's going to happen. You should always be prepared for what happens if they do happen. And so based on the potential for a invocation to potentially hit a failed function, are you losing data? Are you potentially seeing a retry of that data during a recovery? How does that impact your business, for example? So those are all things that you'd want to think about. And really, you want to think about the downstream, right? What happens if a downstream service fails and all of a sudden your Lambda functions can't process requests like you would hope that they could? Is there any potential also for, say, too many invocations or too much data to potentially overwhelm a downstream service? So what kind of controls can you put in place to throttle that? And again, we talked about scaling and concurrency controls earlier. Lastly, in terms of this, thinking about these services, there's a bunch of things that are common across all of them. Pretty much all these services require very little care and feeding in terms of the management of them. They are all pretty much completely fully managed services. The only thing you'd ever have to think about is with Kinesis streams, basically the number of shards that exist in a stream. All these services are HIPAA eligible and PCI compliant. And so if you need to have your infrastructure and your applications meet certain compliance to regulations, these services can help you, at least in regards to these two. They all support very fine-grained permissions via AWS IAM. We haven't spent a lot of time talking about security of these services here today, but all of them, like all services at AWS, have been designed with security in mind, and so the capabilities of those go really deep. And then lastly, all of them have a pay-as-you-go model without commitments. Now, with the exception of the per shard hour cost, the rest of the pricing that you saw here was all about the requests that are coming into the service and then eventually into the downstream service, in this case, Lambda. So it's really easy for you to explore these services without having to think about heavy costs, without having to run any servers, without the ongoing management that involves. So in closing today, there are a lot of different ways to get data between your microservices. We've talked about here today Kinesis, SNS, SQS, and the Lambda API being just a couple of ways. Now, we didn't really talk too much about traditional APIs that you might need to build yourself, but you might need one in some cases. Maybe you've got multiple business units consuming a service internally. Maybe there are potentially more different ways of interfacing with a service that needs to be more interactive. And so you might actually need an API. In this case, we didn't talk about that today. Think through the factor comparisons in terms of scale, durability, persistence, consumption models, retries, and pricing. These are just some of the factors out there that you'd want to think about, but there are definitely more. Now, you'll also probably end up needing more than just one of these. In fact, it's pretty often that we see customers needing to use a couple of these, maybe even all of these in some part of their infrastructure. And depending on the complexity of your infrastructure, there's a lot of things that you could do here. Now, we didn't talk about this here today as well, but there is a tool called the AWS SAM CLI. It allows you actually to locally test on your laptop or workstation, or wherever it might be that you write code, the various ways of invoking Lambda functions. And so you can use the SAM CLI to generate events for Kinesis and SNS and Lambda in order to test it. And then lastly, again, service pricing models make this really, really easy to get started without any sort of commitment, without managing hosts, without having to spend a lot of money between the free tier and, again, just the incredibly low cost at a per usage model here. It's very easy to get started and to play with these services without having to spend a lot of money. Now, almost everything that I talked about here today can be found online at aws.amazon.com/serverless. This is the home for serverless applications and technologies for us here at AWS. You can also find out a lot of stuff here about a bunch of these services at aws.amazon.com/messaging. So I also encourage you to check that out as well. Again, my name is Chris Munns. I am currently a senior and lead developer advocate for serverless at AWS. You can find me at munns@amazon.com or at Chris Munns on Twitter. And now we're going to stick around here and answer some questions via the chat. So keep your questions coming and we'll try to answer them as best as we can. Thanks again for joining us here today and hope to see you in another webinar real soon.